Assalamu alaikum. My name is Ali Khan, roll number 21TE77, and our instructor is Dr. Jamil. Now we move to the lab number 8. The objective of this lab is the implementation and analysis of moving average filter, and the second objective, implementation and analysis of finite impulse response filter Fourier transform and design method. Now we move to word task number 1, which is in the form of questions. So define filter. A filter in the context of digital signal processing refers to a system or algorithm that modifies the characteristic of digital signal. The second, filters are used to extract, enhance, or suppress specific components of a signal based on their frequency, amplitude, and or phase properties. Now we move toward question number 2, which is type of filters. So there are a very type of filters, which is low pass filter, high pass filter, band pass filter, and band stop filter, and the last one is all pass filter. Now we move toward question number 3. What are the time domain parameters for a filter? So here is the parameters is step response, overshoot, and linear phase. So good step response indicate that the filter is settle quickly and smoothly to its final steady state value without significant overshoot or oscillations. This ensures that the filter accurately tracks changes in the input signal and respond promptly to signal transition. The second one is overshoot. Good. Although or negligible overshoot is desirable as indicate that the filter output closely matches the desired response without significant deviation or transient effect. The last one is linear phase. Linear phase is considered beneficial as in ensure that all frequency components of the input signal experience the same phase shift, preserving the signal's waveform and avoiding phase distortion. This is particularly important in applications where phase coherence and signal fidelity are critical. So now we move toward question number 4, which what are the frequency domain parameter for a filter? So here is the frequency domain parameter for a filter is roll off and ripple in pass band and 4 stop band attenuation. Now we move toward question number 5. Discuss the role of low pass filter for filter designing. So there are various role of for a low pass filter. We will discuss a few of them. So the first one is selecting desired frequency while blocking higher frequency, and the second one is preventing aliasing and digital signal processing. Now to move task number 2, plot the signal in time and frequency domain in a log with its magnitude response. The given signal is a x of 1 to 40, which is equal to 0, and the source code. So here in source code, first we define the signal of x, which is x is equal to 0 of 1 to 40, and then plot the signal in the time domain. Here use figure and subplot, and then use stem command and use title, given title, and use x label and y label. So then we use compute or compute the Fourier transform of the signal, which signal is given x is equal to fft of x. and then use compute the magnitude response. Magnitude response is equal to absolute of x, and then use plot the you define plot the magnitude response in the frequency domain, and use subplot which is equal to 3 1 into, use temp command which is magnitude response, and then use title x label and y label, and then define plot the signal in the frequency domain of AFFT plot, and use subplot and stem command title x label and y label. So the output in the output in this figure, here is you can see signal in time domain and magnitude response, and signal in frequency domain. Here is another signal is given which is x of 41 to 120 which is equal to 1. So the source code, first in this source code we define the signal of x is equal to 0 1 to 120, and x is equal to x of 41 to 120 is equal to 1. Then we define the plot the signal in the time domain, which is figure. First we use figure and subplot, then use stem command, and then you given title and x label and y label. Then we compute the Fourier transform of the signal, which is which signal x is equal to FFT of x, and then use uh, compute the magnitude response. Magnitude response is equal to absolute of x, and then use plot the magnitude response in frequency domain, which we use subplot stem title and x label and y label. Then plot the signal in the frequency domain FFT plot. Subplot which is 3 1 and 3. Then use stem which is absolute of x, and then use title, and then use x label and y label. Here is in another signal which is given x of 121 to 161 which is equal to 0. So here in the source code, first we define signal of x, and then plot the signal in this time domain, and then compute the Fourier transform of the signal, and then compute the magnitude response, and then plot the magnitude response in the frequency domain, and plot the signal in frequency domain FFT plot. So the output in the figure, here you can see signal in time domain and magnitude response and frequency signal in frequency domain. So here is the another signal which is x of 121 to 161 which is equal to 0. So the source code here, first we define signal of x, and then add noise to x, and then plot the noise signal in the time domain, and then compute the noise, and then compute the magnitude response of the noise signal, plot, and then plot the magnitude response of the noise signal in the frequency domain, and then plot the noise signal in the frequency domain FFT plot. In the output you can see noise signal in time domain and magnitude response of the noise signal, and then noise signal in frequency domain. So there is another signal x of x noise is equal to x plus 0.5 multiply range in size x of x. So in the source code, first we define signal of x, and then add noise to x, and then define the moving average filter cutoff coefficients, and then apply the moving average filter to x noise, and then plot the filter signal in the line time domain, and then compute the Fourier transform of the filter signal, and then compute the magnitude response of the filter signal, and then plot the magnitude response of the filter signal in frequency domain, and then plot the filter signal in the frequency domain FFT plot. So in the output, you can see in the figure, this is a filter signal in time domain, and this is magnitude response of filter signal, and this is filter signal in frequency domain. Then here is a question which we ask that apply 3 top symmetrically around moving average filter on signal X noise and observe the time and frequency domain parameter. So source code here which we define signal of X and add noise to X, and then define the moving average filter coefficient, and then apply the moving average filter to X noise, and then moving filter signal in the time domain, and then compute the Fourier transform of the filter signal, and then compute the magnitude response of the filter signal, and then plot the magnitude response of the filter signal in frequency domain, and then plot the filtered signal in the frequency domain FFT plot. So in the output figure, here is filter signal in time domain, and here is magnitude response of filtered signal, and here is filter signal in frequency domain. So now we move to question. Another question which we ask from us that apply 11 top symmetrically around moving average filter on signal X noise and observe the time and frequency domain parameters. So here is the source code. In the source code, first we define the signal of X and then add noise to X, and then define the moving average filter coefficient, and then apply the moving average filter to X noise, and then plot the filter signal in the time domain, and then compute the Fourier transform of the filter signal, and then compute the magnitude response of the filter signal, and then plot the magnitude response of the filter signal in frequency domain, and then plot the filter signal in frequency domain FFT plot. So here is the output. So in the output figure, this is a filter signal in time domain, and this is magnitude response of filter signal, and this is filter signal in frequency domain. So here is another question which apply 25 top symmetrically around moving average filter on signal X noise and observe the time and frequency domain parameter. So here in the source code, first we define a signal of X, and then you use noise, add noise to X, and then define the moving average filter coefficients, and then apply the moving average filter to X noise, and then plot the filter signal in the time domain, and then compute the Fourier transform of the filter signal, and then compute the magnitude response of the filter signal, and plot the magnitude response of the filter signal in frequency domain, and then plot the filter signal in the frequency domain FFT plot. In the output figure, here you can see filter signal in time domain and magnitude response of filter signal and filter signal in frequency domain. So now we move to our task number 3. Repeat example 7.2 for uh, 17 top coefficients. So here is the source code. Contains n is equal to 17 number of taps, and fc is equal to 800 cutoff frequency in hertz, and fs is equal to, which is sampling frequency, is equal to 8000. So this is sampling rate in hertz, and then calculate the normalized cutoff frequency between 0 and 1, and then calculate the filter coefficient using the Fourier transform method, and this is the Fourier transform method, and display the filter coefficients and display of h, and then determine the transfer function using the filter coefficient b is equal to h and a is equal to 1, and then convert the transfer function to symbolic form for equation magnitude manipulation. Since is equal to z and h of z is equal to fully